Hello everyone, welcome to this lecture. So, just to recap, in the last lecture we have seen a candidate public key encryption scheme, CPA secure public key encryption scheme, namely Algol encryption scheme. In this lecture and the next lecture we will discuss another candidate public key encryption scheme based on a different hard problem which we call as RSA assumption, which will lead us to another public key encryption scheme, namely the RSA public encryption scheme. So, to understand the RSA assumption, let us first try to understand the set Z and star. So, Z and star basically is the set of integers modulo n which are co-prime to the modulus n, namely Z and star is the collection of all elements little b in the range 1 to n minus 1 such that the element b is co-prime to the modulus n, namely their GCD is 1. So, for example, the set Z10 star is nothing but the elements 1, 3, 7, 9, because all these elements 1, 3, 7, 9 they are co-prime to the modulus 10. And it is easy to see that if my modulus n is prime, then the set Z n star basically consists of all the elements 1 to n minus 1. So, a well known fact from the number theory whose proof I am skipping is that this set Z n star along with the operation multiplication modulo n constitutes a group and satisfies all the axioms of the group. So, for instance, I have drawn the matrix for the elements in Z10 star, namely 1, 3, 7, 9, and the result of performing the operation multiplication modulo 10 for any pair of elements from this set, and now you can see that all the axioms of the groups are satisfied, and that is why this is a group. And moreover, a well known fact from the number theory is that we have polytime algorithms for computing the multiplicative inverse, which I denote by a power minus 1 for any element a in this set Z n star, and there is a well known algorithm for that which we call as Euclid's extended Euclid's GCD algorithm, which we will discuss in one of our subsequent lectures. And the running time of that algorithm is polynomial in the number of bits that we need to represent the modulus n. So, let us next discuss Euler Totient function phi function. So, the Euler's Totient function, which is denoted by this symbol phi of n, is basically the cardinality of your set Z n star, namely it is the number of elements in the set 1 to n minus 1 which are co-prime to your modulus n. Now, some of the well known facts again borrowed from number theory are as follows. So, if n is a prime p, then the set phi of then the value of phi of p is nothing but p minus 1, because there are exactly p minus 1 elements which are co-prime to p. On the other hand, if n is the product of two distinct primes p and q, then phi of n is nothing but p minus 1 times q minus 1. That means, there are these many elements, namely p minus 1 times q minus 1 elements in the range 1 to n minus 1 which will be co-prime to your modulus n. To verify that, let us take an example, say n is equal to 10, which you can write as the product of 2 and 5, where 2 and 5 are primes. So, your p is 2 and your q is 5, then we know that there are 4 elements in the set Z10 star. So, phi of 10 should be 4, and that is nothing, 4 is nothing but p minus 1, namely 2 minus 1 multiplied by q minus 1, which is 5 minus 1. And finally, another interesting property which we will use from number theory is that for any element little a in the set Z n star, a to the power phi of n modulo n is 1. That means, if n is a prime p, then this phi of n is nothing but p minus 1. So, we get a to the power p minus 1 modulo p to be 1, and this property or this result is also called as Fermat's little theorem. And we also get from due to this fact a corollary that if you have any element a belonging to the set Z n star, then a to the power x modulo n is exactly the same as a to the power x modulo phi n modulo n. That means, in the exponent you can reduce the exponent x to x modulo phi n. So, the reason this corollary is true is that if your x is anyhow less than phi of n, then both LHS and RHS are same, but if your x is more than phi n, then to compute a to the power x modulo phi n, what you can do is you can have you can rewrite a to the power x as several batches of a to the power phi n in the exponent, a to the power phi n depending upon the relationship between x and phi n, and the last batch will have a to the power x modulo phi n in the exponent and everything in the base modulo n. Now, we know that a to the power phi n modulo n is 1, that means each of these batches where you have full a to the power phi n modulo n, they are going to give you the answer 1. So, all these batches are going to give you the answer 1 1 1 1 1 and 1 multiplied by 1 is going to give you 1. So, you are finally left with the last batch which has a to the power in the exponent x modulo phi n. So, that is how we get this corollary. So, with all this mathematics in place, now let us try to understand the RSA permutation. So, this RSA permutation is a mapping from the set z n star to z n star. So, the way this permutation is defined is as follows. So, imagine you are given a exponent e which is greater than 2 such that the exponent e is co-prime to your value phi of n. So, I stressed it is co-prime to phi of n, not to n. Now, a well known fact from number theory is that if you have an e which is co-prime to phi of n, then you can find out the multiplicative inverse of that e modulo phi of n. In general, if you have two numbers say a and b such that GCD of a and b is 1, that means a and b are co-prime to each other, then you can always find the multiplicative inverse of a modulo b. So, my modulus in this case is phi of n, because E is co-prime to phi n, and if E is co-prime to phi n, by using the extended Euclid algorithm I can find a D where E and D constitutes their mutual multiplicative inverses. That means E times D modulo phi of n and D times E modulo phi of n is 1. Now, the RSA permutation is as defined as follows. To go in the forward direction, the function is f sub e, and to compute the value of f sub e on a value x where x is a member of z n star, we basically compute x to the power e and do mod n. On the other hand, the reverse direction function is basically a function of d, namely f sub d y, and this function is basically, if I want to compute f sub d of y, I will compute y to the power d and then perform mod n. And I claim here that the function f sub d is the inverse of the function f sub e and vice versa. So, for that consider any arbitrary x here belonging to z n star and say I map it to y as per the function f sub e. So, my y is nothing but x to the power e, and now let us see what we obtain by reversing this value y as per the function f d. If I reverse this y as per f d, then I obtain x to the power e mod n and then whole raised to power d mod n. So, I can take the overall mod outside and I obtain that this is same as x to the power e times d modulo n, and by using the corollary that we have stated in the last slide, x to the power e d modulo n in the exponent I can reduce this exponent e times d to e times d modulo phi of n. And I know that e times d modulo phi of n which is there in the exponent gives me value 1, because I have chosen e and d such that they are multiplicative inverse of each other. So, in the exponent e times d modulo phi of n reduces to 1. So, hence I obtain that this x times e d modulo n is nothing but x modulo n, and since I have chosen my x to belong to the set z n star, that means x is anyhow less than n, and if x is less than n, then x modulo n gives you x, the effect of mod does not happen at all. So, this proves that your function f d and f e are mutually inverse of each other. I also prove here now that my function f of e x is a bijection, and for that means it is a 1 to 1 onto mapping, and for that let us consider an arbitrary pair of inputs x 1 comma x 2 from the set z n star and say the resultant images of x 1 and x 2 as per the function f sub e are y 1 and y 2. Now, if y 1 and y 2 are same, that means x 1 to the power e modulo n is same as x 2 to the power e modulo n. That means, if I raise both the sides to the exponent d, I get x 1 times x 1 to the power e d modulo n is same as x 2 to the power e d modulo n, and this basically means that x 1 is equal to x 2, because x 1 to the power e d modulo n is nothing but x 1 and x 2 to the power e d modulo n is nothing but x 2. So, that means if I take an arbitrary x 1 x 2 mapping to the same y 1 and same y, then basically I end up showing that x 1 is equal to x 2, and hence I overall get that my function f e is a permutation here, right. Now, let us discuss a related assumption which will be related to the RSA assumption which we will finally discuss. So, this is called a factoring assumption, and the intuition here is the intuition behind this assumption is that if you are given the product of two large arbitrary prime numbers, it turns out that finding the prime factors is indeed a difficult task, because and this is a very widely known well studied problem, studied over several centuries. Until now we do not have any efficient polytime algorithms for factorizing a product of two arbitrary prime numbers if those prime numbers are chosen arbitrarily. So, this intuition or the hardness of this problem is going to be formalized by an experiment, and for that experiment let us first define an algorithm which we call as gen modulus algorithm, which basically picks two random n bit prime numbers say p and q, and there are well known algorithms to pick random prime numbers. I am not going into the exact details at how exactly you pick those two random prime numbers in poly of n time. You can refer to the book by Carson-Lindell for the exact algorithm. Now, once p and q are chosen, you compute the modulus, namely big N, which is the product of p and q. Now, the factoring assumption with respect to the gen modulus algorithm is modeled as an experiment which we call as factor experiment, and the rules of the experiment are as follows. The challenger runs the gen modulus algorithm, generates the parameter n, p and q, and the challenge is thrown to the adversary, namely big N, and the challenge for the adversary is to come up with its prime factorization, namely p and q. So, it submits to a pair of numbers p dash and q dash, and we say that the output of the experiment is 1, namely adversary has won the experiment if indeed the pair p dash comma q dash is exactly the same as the prime factorization of your modulus big N. And we say that the factoring assumption holds with respect to our algorithm gen modulus if for every polytime adversary the probability that adversary could come up with the correct factorization of the modulus n is upper bounded by some negligible function. Notice that there is always a guessing strategy by an adversary. It can guess some p dash and q dash, and with non-zero probability it may indeed be the correct factorization of n. What we want is basically that no polytime adversary should be able to do anything better than that. That is basically the intuition of this experiment. Now, finally, let us see the RSA assumption here. So, it turns out that factoring assumption, even though it looks like a candidate one way function, that means if I give you the product of two arbitrary large prime numbers and challenge you to come up with the factorization, then that looks like a candidate one way function, but just based on this candidate one way function we cannot directly get a practical public key crypto system. So, to get around that we introduce a related problem which we call as an RSA problem, whose difficulty is related to the hardness of the factoring problem. So, this RSA problem is described with respect to another parameter generation algorithm which we call as gen RSA. So, what this gen RSA algorithm does it first runs the gen modulus algorithm and pick up random primes p and q of size little n bits each and multiplies them to get the modulus big N. And now, it computes the value of phi of n, and it is computable because phi of n is nothing but the product of p minus 1 and q minus 1. Then this gen RSA algorithm picks an exponent e such that e is relatively prime or co-prime to phi of n, and since e is co-prime to phi of n, by running the extended Euclid's algorithm the multiplicative inverse d of e modulo phi of n is computed. And overall this gen RSA algorithm now outputs n, p, q, e and d. Now, intuitively the RSA problem is if you are given just a public modulus n and a public exponent e and a random element y from the Zn star set, then the challenge for you is to compute the eth root of y modulo n without actually knowing the value of d or without knowing the prime factorization of n. I stress that the challenge is to compute the eth root modulo n, because if I just challenge you to compute the eth root without modulo n, that is very easy to do that. The challenge here is to compute the value of eth root of the random y modulo n, which is formalized by this experiment which I call as RSA inverse experiment. The experiment is as follows: the challenger runs the gen RSA algorithm to generate the parameters n, p, q, e, d. A random y is chosen from the set Zn star. Again, if you are wondering that how how picking up a random element from the set Zn star is possible in poly of little n time, well, that is possible. You can see the reference by, you can see the book by Katz-Lindell where the algorithm is given how to pick random elements. Now, the challenge for the adversary is to find out the eth root of this random y just based on the knowledge of public modulus n and the public exponent e. So, it has to output a group element say x, and we say that adversary has won the experiment or the output of the experiment is 1 if and only if x is indeed the yth root of x is indeed the eth root of the random y modulo n, namely if x to the power e modulo n is y. And we say that RSA assumption holds with respect to this Gen RSA algorithm if for every polytime algorithm participating in this experiment, the probability that it can come up with the correct eth root of a random y is upper bounded by some negligible probability. So, now let us try to compare the RSA assumption and factoring assumption, because on a high level they might look similar to you. So, on your left hand side you have the factoring experiment where the challenge for the adversary is to factorize or come up with the prime factorize of the public modulus n. On the right hand side you have the experiment modeling the RSA problem where adversary is now given some extra information as part of its challenge, namely it is given the public exponent e and a random y from the set z n star, and its goal is to come up with the eth root of the random y modulo n. It turns out that we can prove that if RSA assumption holds, then factoring assumption also holds, and this can be proved by contrapositive. Namely, if we assume that factoring is computationally easy, that means it is possible for a polytime adversary to come up with a prime factorization p comma q of a modulus n, then once you factorize your modulus n into its prime factorization p and q, then you can easily compute phi of n, because phi of n is nothing but p minus 1 times q minus 1. And if phi of n is computable in polytime and anyhow e is given to you, then by running the extended Euclid algorithm you can yourself compute the multiplicative inverse of e, namely d. And once you compute d, the eth root of y is nothing but y to the power d modulus n, y to the power d modulo n. That means this implication is indeed true. On the other hand, let us try to consider the relationship between the factoring assumption and RSA, in the sense, can we say that if factoring assumption holds, then RSA assumption holds, and we do not have any answer for this. That means, we cannot prove that if RSA assumption does not hold, then factoring assumption does not hold. It is a big open problem, because there might be a way to efficiently solve the RSA problem without actually factoring your modulus. Because one of the ways of solving the RSA problem might be to factorize your n, and then once the factorization is known, come up with the value of d and so on. But that need not be the only way to solve the RSA problem. There might be other ways to compute to solve the RSA problem in polynomial amount of time without actually factorizing your modulus. And in that sense, making the RSA assumption is a very stronger assumption compared to making the factoring assumption, because difficulty wise the factoring problem is a more, looks like a more challenging problem, more difficult problem than solving the RSA problem. So, now finally let us discuss that how exactly you can visualize your RSA permutation as a trapdoor permutation, because in our next lecture we are going to treat our RSA permutation as a trapdoor permutation, and we will see the how we can formulate an instantiation of public key encryption scheme from this RSA permutation. So, for that recall the definition of one way trapdoor permutation. So, it is a function from a set fancy x to the set fancy x, which is easy to compute for any input of the domain, but difficult to invert for any random input from the codomain until and unless you are given with a special trapdoor information. So, this is formalized by saying that we so more formally we have a trapdoor permutation scheme over the set fancy x, which consists of a key generation algorithm, a trapdoor, a function f and its inverse, where the generation algorithm, parameter generation algorithm will output a public parameter and a secret parameter. The function f is basically a keyed function keyed by the public key pk, and it takes values from the set fancy x and it gives you an output from the fancy set x from the fancy x set, and it is a deterministic algorithm, and a corresponding inverse algorithm is operated by a secret key. So, your secret key is basically acting as a trapdoor information here, and using this trapdoor information you can correctly invert any y from the codomain, namely the set fancy x. And the correctness property that we require from a trapdoor permutation scheme is that for every pair of parameter generated by the generation algorithm, for every x from your domain, if you compute the value of f with the key with the public key under that on that input x and say obtain the y output, and now if you invert that y with the secret key xk, you should get back the x. And the second requirement is the one wayness requirement, which basically states that your function f should behave like a one way function if you even if an adversary knows the value of the public parameter pk. So, now let us see how we can visualize the RSA permutation from the set Zn star to Zn star as an instantiation of the trapdoor permutation. So, basically RSA trapdoor permutation consists of 3 algorithms. The parameter generation algorithm is nothing but the gen RSA algorithm, namely it picks uniformly random n bit prime numbers p and q, compute the modulus big N, and then compute the size of Zn star, namely phi of n. It picks a public exponent e such that e is co-prime to phi of n. Since e is co-prime to phi of n, by running the extended Euclid algorithm, multiplicative inverse of e modulo phi of n is computed, and the public parameters are n comma e and the secret parameters are n comma d. The forward direction function, namely the function f sub RSA, and operated with the public key n comma e is as follows. To compute the value of this function f sub RSA on an input x, basically you just output x to the power e modulo n, and x to the power e modulo n can be computed in poly of little n time. We will see later on how exactly this group exponentiation can be computed in polynomial in n amount of time. On the other hand, if you have a trapdoor, namely a secret parameter n comma d, and if you want to invert any given y from the set Zn star, basically you have to compute y to the power d modulo n. Now, let us see whether this trapdoor RSA trapdoor permutation indeed satisfies the requirement of a generic trapdoor permutation scheme. So, the correctness requirement states that it should hold that x to the power e followed by raising it to d modulo n should give me by x, and well we already have proved that indeed that is the case when we showed that the function f and the inverse RSA function are inverse of each other. On the other hand, the one wayness property from this RSA permutation requires that anyone who knows just the public parameter, namely say n comma e, but does not know the trapdoor information say d, without the knowledge of the trapdoor information, it should be difficult to compute the eth root of any random y. And it turns out that indeed that is the case if the RSA assumption holds with respect to your parameter generation algorithm. That means, if indeed the RSA problem is difficult to solve with respect to this RSA parameter generation algorithm, then this so called RSA permutation can be viewed as an instantiation of your trapdoor permutation. So, recall that in one of our previous lectures we had seen that how generically we can convert a trapdoor permutation scheme into a key agreement protocol with weak secrecy notion. And now, if we instantiate a trapdoor permutation by an RSA trapdoor permutation, then by using the RSA trapdoor permutation we actually obtain an RSA key exchange protocol, right, which gives you a weak secrecy notion, namely the resultant key is going to be known to sender and the receiver, and adversary will not know the full key in its entirety. On the other hand, there exists the discrete log function that we had discussed earlier. It cannot be viewed as an instantiation of the trapdoor permutation, because we know the forward direction function, namely say g to the power x can be treated as your forward direction function, but we do not know what should be the corresponding trapdoor information using which we can invert back this function, and that is kind of a big challenging problem which is there. On the other hand, in the context of RSA permutation, we have the corresponding trapdoor associated, namely the decryption, namely the exponent d, which is the multiplicative inverse of e modulo phi of n. So, that brings me to the end of this lecture. In this lecture, we have introduced the RSA assumption, and we have seen the relationship between the RSA problem and the factoring problem. Thank you.